After the detailed analysis of basic fundamentals of statistical mechanics, now today we are going to start the first basic theory of statistical mechanics. Actually, as I have told you in the introductory lecture, that basically we say that the statistical mechanics is of two types. First one is called classical statistical mechanics and another is called quantum statistical mechanics. So this is the first lecture on the basic theory of classical statistical mechanics. Actually, classical statistical mechanics is based on a particular law which is called Maxwell Boltzmann distribution law, or all these theories are discussed in terms of a particular function which is called Maxwell Boltzmann distribution function. So in this lecture we are going to start the Maxwell Boltzmann statistics. Okay, this is a very important chapter for you, and so watch all the videos of this series seriously, and after that you will feel that your concept regarding the classical statistical mechanics, particularly the Boltzmann statistics, will be very clear to you. So in this regard, first of all, we are going to discuss what is this Maxwell Boltzmann distribution function. I have written here MB. This is actually the short form of Maxwell Boltzmann. So what is Maxwell Boltzmann distribution function? What will be expression for it? And how can we find the expression for this Maxwell Boltzmann distribution function? Some authors also write this result as Maxwell Boltzmann distribution law. Although the Maxwell Boltzmann distribution law regarding the molecular speed and molecular velocity of gas molecules you also study, and already I have provided videos on the distribution law of molecular velocity and molecular speed in the playlist of thermodynamics of my channel. Okay, but here we will see the purely statistical concept of this Maxwell Boltzmann distribution statistics. Okay, first of all, you should know, as I have told you earlier in the introductory lecture, that when you talk about Maxwell Boltzmann statistics, that means you are talking about classical statistics. And in classical statistics, as I have told you earlier, that the particles of the systems are considered identical, but they are distinguishable. Okay, this is a very remarkable fact, that in this statistics, whenever we consider the particles of a system, all the particles will be identical, but they can be distinguished, not indistinguishable. When we will study quantum statistics, you will see that in quantum statistics the particles are identical but indistinguishable. But here the particles are distinguishable, so we always mark the particle or always label the particle by a proper name, like particle A, particle B, particle C, and you can distinguish between those particles. Okay, as you know that a spin is a quantum mechanical property of the particle, and when we study classical mechanics, there is no role of a spin, because you have definitely an idea that a spin has no classical analog. So whenever we will talk about the distribution of particle in different quantum states or in different phase cells in the statistical mechanics, the spin will play no role. So we will never take into account the spin of the particle. Whatever the spin of the particle, that does not matter when we actually discuss the classical statistics. So I have mentioned it here that no role of spins of the particle. Okay, but this spin will play a vital role when we will study the quantum statistical mechanics, because in quantum statistical mechanics, the distribution of particle in different quantum states is actually governed by the spin of the particle. Okay, And but in this Maxwell Boltzmann statistics or classical statistics, a spin has no role in distributing the particle in different quantum states. So these facts you should remember here. Actually, our first problem, which in this lecture we are going to discuss, as I have told you, is to know about the Maxwell-Boltzmann distribution function. So what is this Maxwell-Boltzmann distribution function? What will be the expression for it? What are the factors affecting this function? All these things will be discussed in this lecture. Okay? And for this, let us consider an assembly, or you can say an ensemble of particles, and we consider that the total number of particles in this assembly is n. When you say particles, as I have told you, all the particles will be identical but distinguishable. Okay. In fact, we also consider that all these n particles interact with one another very weakly. Or in other words, you can also say that this system is a system of non-interacting particles. There is no interaction between the particles. Okay? And when there is no interaction between the particles, there will be an ideal example of perfect gas. Because you know, in case of a perfect gas, the molecular interaction is zero, no molecular interaction takes place. So, for a particular example, you may keep in your mind that there is a system of ideal gas, okay, and this system is also isolated. It has no relation with the surrounding, that is, there is no exchange of either the particle or the energy between the system and its surrounding. So the system which is weakly interacted, or you can say which is constituted by non-interacting particles, are isolated. And we also assume that all these particles are governed by the same Hamiltonian H. Okay? So in brief, you can say that we consider an assembly of n weakly interacting particles governed by the same Hamiltonian H. Okay? Now, we consider that there are n1 particles with energy E1, n2 particles with energy E2, and so on, nn particles with energy En. We consider. It means there is a group of n1 particles, and all these n1 particles have energy E1. Okay? Similarly, there is a group of n2 particles among these n, and each of the particle of the group n2 has energy E2. So E2 is not the total energy of n2 particles, but it is energy of individual particle. Okay. All these things you can see here from this table, that we have considered that this is number of particles. So there is a group of particles having number n1, and among these n1 particles each have energy E1. Okay, and at the same time we also consider that this energy level E1 in which all these n1 particles are contained is G1 fold degenerate. It means the energy eigenvalue E1 has a degeneracy of G1. When you say that E1 energy eigenvalue has degeneracy G1, or this energy level is G1 fold degenerate, what does it mean? It means in this energy level, let us consider that this is our energy level which is E1. Okay. In fact, in this energy level, there will be G1 number of quantum states in which these n1 particles will be distributed. So when you say that G1 is the degeneracy of energy eigenvalue E1, that means there are G1 quantum states, or in terms of classical statistics, you can also say this G1 represents the number of phase cells in this energy level E1. Okay. Similarly, N2 is the number of particles each having energy E2, and this energy level is G2 fold degenerate. We consider it. Okay. And similarly, you can say that there are Ni particles each with energy Ei, and this energy level is Gi fold degenerate. Okay, we consider it. Okay. So this configuration which you have considered, that N1, N2, so on, Nn, actually here this small n represents the number of energy levels. This is number of energy levels. Okay. So this configuration, which is written like this N1, N2, so on, Nn, actually this configuration, among these configurations, actually there will be maximum number of the configuration which will have maximum number of microstates is known as most probable macrostate or most probable configuration. Okay. Now, as you can see that this in general, if you talk about in general case, that this Ni particles each with energy Ei are distributed in Gi quantum states. Okay. So you can say that in Gi quantum state, the total number of particles distributed is equal to Ni. So if we want to find what will be the average number of particles in one quantum state, what will be that number? Since Gi quantum number contains Ni particle, so in one quantum state or in one phase cell, the average number of particle will be Ni divided by Gi. So this Ni divided by Gi, that is number of particles divided by the degeneracy of the energy eigenvalue of the particle, that represents the average number of particle per quantum state or per phase cell. You can also say instead of quantum state, you can say phase cell. Actually, this number of particles, average number of particle per quantum state, which is equal to Ni divided by Gi, this is actually denoted by the symbol F of Ei. Actually, this depends on the energy eigenvalue, and that is called occupation probability. All these things which I have just clarified to you, I have mentioned it here for your convenience. Okay. So you can see I have written that Ni particles with energy Ei are distributed in Gi quantum state or phase cells. So the average number of particles per quantum state, that will be equal to Ni divided by Gi. Okay. As I have explained that in Gi quantum state, the number of particles are actually Ni. So in one quantum state, the number will be simply Ni divided by Gi. And this average number of particle per quantum state is denoted by the symbol F of Ei, because this will depend on the energy eigenvalue Ei. Okay. And this quantity is called occupation probability. This is called occupation probability. Okay. Now, since we are talking about classical statistics, and you know in classical mechanics, the energy eigenvalues of a system are almost continuous. Actually, you cannot talk discrete energy levels or discrete energy eigenvalue in classical statistics. Actually, all these energy levels form a continuum. It means the energy eigenvalues are not discrete in practice in classical mechanics, but they are actually continuous. So in that condition, since the energy level is not discrete but continuous, so you cannot talk the ith energy level. So we will simply drop this subscript I, and then we will write this f of ei by the symbol f of e. And when you write this symbol f of ei like f of e, that is called actually the distribution function. And when you talk about the classical statistical mechanics, then this distribution function is called Maxwell Boltzmann distribution function. Okay. Now actually our prime aim is to find the expression for this distribution function. Okay. So now we will try to understand how we can find the expression for this distribution function. Okay. So now we are going to compute the number of microstates and the distribution function f of e. Okay. Now as you know that the particles of this system, which is actually a classical system, are distinguishable, as I have told you. So in this condition, you know that out of n particles, when you have considered that there are total n particles, and you have also considered that out of n particles, n1 particle has energy E1. Okay. N2 particles have energy E2. Okay. And so on. So the total number of ways in which this group can be formed, how we can form this group, how many ways will be the forming of this group. You have already studied when I have discussed the macrostate and microstate, that since the particles are distinguishable, so the ways in which the group n1, n2, so on nn of particles can be chosen, can be formed from n particles, and that number will be given by W1 equal to n factorial divided by n1 factorial times n2 factorial. You have already studied this fact in the earlier lecture. So this W1 represents the number of ways in which this group like n1, n2, n3 can be formed. And this expression can be written as n factorial divided by product of ni factorial, where I runs from 1 to n. Okay. Actually, product is denoted by this symbol capital pi, and this represents the product of different values of ni for the limits I equal to 1 to n. Okay. So W1 is the total number of ways in which these groups of n1, n2, so on nn particles can be formed. Okay. Now, after forming this group, or after knowing the number of ways in which this macrostate or this configuration can be formed, now our prime problem is to distribute these particles, that is n1 particles, n2 particles, n3 particles, among the different quantum states. As you have seen earlier, that n1 particles are to be distributed in G1 quantum states or G1 phase cells. Okay. Similarly, n2 particles are to be distributed in G2 quantum states. Okay. In general, you can say our problem is to distribute Ni particles among the Gi quantum states. You can think that there is a hotel. Let us consider there is a practical example. For a practical example, you can consider there is a hotel. Okay. And there are 10 customers who have to accommodate in the rooms of the hotel, and the number of rooms in the hotel, let us say, is 50. Okay, so if 10 customers are to be distributed among the 50 rooms of the hotel, how many ways can be of the distribution? This is just the problem. Okay, there is no restriction in this case that which customer will remain will stay in which room. There is no restriction. So let us see here. In fact, inside this box, I have assumed that there are Ni particles. This dot represents the different particles, and the total number of particles is Ni. This is in fact in the energy level Ei. But this energy level, as you know, is Gi fold degenerate. It means what? It means in this energy level there are actually total I compartments, or you can say total I phase cells or quantum states. So these small spheres I have denoted for the quantum states. So this is your first quantum state, this is second quantum state, this is third quantum state, and this is ith quantum state. Okay, this is ith quantum states, and ith means Gi. Gi is the number of quantum states. Okay, now if you consider that these Ni particles selected from the energy Ei are to be distributed among these Gi quantum states, in how many ways we can distribute it? Actually, there is no restriction that which particle will remain in which quantum state. So you can think that the first particle, let us select, this is considered, this is first particle, and this first particle can be put into the first quantum state. This can also be put into the second quantum state. This can also be put into the third quantum state, and this can also be put in the ith or gith quantum state. Okay, so the first particle out of this Ni particles can be put in Gi ways. This first particle among Ni can be placed in Gi ways among these Gi quantum states. Similarly, when you will consider the second particle, let us consider this is second particle. That second particle can also be put in different quantum states in Gi ways, and in this way you can say that any particle from these Ni particles can be put into these quantum states by Gi ways. So can you say what will be the total number of ways by which these Ni particles can be distributed among these Gi quantum states? That will be simply, since the number of particle is Ni and number of quantum state is Gi, and each particle can be placed in these quantum states by Gi ways. So the first particle will be distributed in Gi ways, second will be also in Gi ways, third will be also in Gi ways, and just like that the nith last particle will be also placed by Gi ways. Actually this number will be Ni. So you have to multiply this Gi Ni times. So Gi times Gi times Gi up to Ni terms will be what? That will be simply Gi to the power Ni. Okay. So you can say that the total number of ways in which these Ni particles can be distributed among the Gi quantum states or among the Gi phase cells, that number is simply equal to Gi to the power Ni. Okay. So in the similar manner, you can say that the number of ways in which n1 particle will be distributed among the g1 quantum state, and that number will be what? That will be g1 to the power n1. Similarly, n2 particles when distributed among the g2 quantum states, the total number of ways of distribution will be g2 to the power n2, and so on. Okay. So in this way, if you want to find that for different values of I, uh, you can find the total number of arrangements will be what? The total number of arrangements then will be W2, and that will be equal to G1 to the power N1 into G2 to the power N2, and so on, Gn to the power Nn. Okay. And this can be written in compact form by the use of this sign of product, that W2 is equal to product of Gi to the power Ni, where I runs from 1 to n. Actually, this small n, as I have told you, represents the number of energy levels. Okay. So you can see that actually we have seen that there are W1 ways. You have calculated W1. There are W1 ways of forming the group N1, N2, so on Nn. There are W1 ways for forming this group. Okay. And once the group is formed, there are W2 ways, this W2, there are W2 ways of distributing the individual particles in different quantum states. Okay. So the total number of microstates corresponding to the macro state or the configuration N1, N2, so on Nn will be what? That number will be actually equal to product of these two probabilities. So W is equal to W1 into W2. Actually, this total number of ways of distributing all the particles in different quantum states is also known as thermodynamic probability. This is known as thermodynamic probability for the most probable macro state. This is known as thermodynamic probability of most probable macro state. So you can see that the thermodynamic probability of the most probable macro state, or the total number of microstates corresponding to the configuration N1, N2, and so on, that will be equal to W1 times W2. And you have seen that W1 is equal to this much. This is your W1. This is n factorial divided by product of Ni factorial, where I runs from 1 to n. And W2, you have just obtained that W2 is product of Gi to the power Ni. Okay. So in this way, I hope you have understand how we can distribute these system of n identical particles which are distinguishable and non-interacting among the different quantum states. Okay. Now, to find the expression for the distribution function, there will be some mathematical steps, and you have to follow that mathematical steps to obtain the expression for the distribution function. One thing is very interesting here, that all these mathematical steps will be same whenever you will discuss even the Bose-Einstein statistics or the Fermi-Dirac statistics. The distribution function in those quantum statistics will be also obtained by the same mathematical step. So let us start to know how we can now find, after knowing this thermodynamic probability or the number of microstates corresponding to the most probable macro state, the expression for the distribution function or Maxwell Boltzmann distribution function. For this, in first step, we simply take the natural logarithm of this equation 3. So let us take the natural log. When you say natural log, it means logarithm at the base e. So this will be simply log w equal to what? Log n factorial plus summation over I 1 to n log gi to the power ni minus summation over I 1 to n log ni factorial. You should know that when you will take a log, then this product will be changed into summation. Okay? And you know that log a into b is log a plus log b. So this is actually log n factorial plus summation I 1 to n log gi to the power ni. And log a by b is log a minus log b. So this is minus here. Okay? And whenever you will take the logarithmic value of product of quantities, then that will be actually that will change into summation. Okay. Now, in the previous lecture, we have discussed a Stirling formula, and I have told you that this Stirling formula finds its application always in a statistical theory. So you can see here there is a need of a Stirling formula. You have learned that when n is a very large number, then log n factorial is equal to n log n minus n. This is called a Stirling formula. And this formula holds only when n is very large. Now here actually we are talking about a classical system, and a classical system actually consists of a very large number of particles. So this n or this ni is very large, and therefore we can simplify this logarithmic value of n factorial and ni factorial by Stirling formula. So you can write, instead of this log n factorial, you can write n log n minus n. You can write. Now you know that this log gi to the power ni is equal to ni log gi. Okay. I am not saying this summation, it is understood. And again, this log ni factorial by the use of a Stirling formula can be written as ni log ni minus ni. Okay. Now let us simplify this result. You can see I have written this at each. This is n log n minus n. The second term is also at each. Okay. And in this third term, you can see there will be summation I 1 to n ni log ni, and this minus and this minus will be now plus, and as you know, summation over I 1 to n ni is equal to n. Actually, summation ni means what? It represents the total number of particles, that is n1 plus n2 plus n3 plus so on plus nn, and that is equal to n. So instead of summation over ni, I have written here ni, and you can see this minus ni and this plus ni will cancel out. Okay. So after cancelling this n, what is your result? So that result will be now written. You can see the first term remains n log n, second term will be summation ni log gi, third term will be summation ni log ni. Okay. So write these terms here. So you can see ln w is equal to n log n plus summation over I ni log gi minus summation over I ni log ni. Okay. But as you know that we have calculated W, which is actually the maximum number of microstates corresponding to the most probable macrostate. Okay. And so for the most probable macrostate, This W since represents the maximum number of microstates, or this is the maximum value of thermodynamical probability. So W is maximum, and if W is maximum, its logarithmic value ln W will be also maximum. And since ln W is maximum, so its differential will be what? Its differential will be 0. Okay? This is just a simple concept of calculus, that if ln W is maximum, its differential or its change will be 0. You can also say change of ln W. Now here in equation 4, you know what is this ln W. Now you have to take the differential or the change of the terms in RHS of this equation 4. Now see, the first term in equation in RHS of 4 is n ln n. But as you know, the total number of particle n is constant. So the first term n ln n is constant, so its differential will be 0. So I have written here 0. Okay. Now the number of quantum states in a given energy level Gi is also constant. Although for different energy level, the number of quantum states or number of phase shell is different. But for a given energy level or for a given energy eigenvalue, the number of quantum states is fixed, or degeneracy of a energy level is fixed. So Gi is also constant. So when you will take differential of this second term, that is summation Ni log Gi, then log Gi will be treated as a constant factor. Okay. So there will be only differential of Ni, and that is simply dNi. Okay. Minus. Now we will take the differential of this third term in RHS of this equation 4. Here Ni represents the number of particles in a particular energy level, and for different energy levels its value is different. So here this Ni is actually variable. So log Ni is also variable. So actually in this third term there is a product of two functions. First function is Ni and the second function is log Ni. So we will follow the rule of differentiation of product of two functions here. So when you will keep this Ni at each, there will be differential of log Ni, and plus now take this log Ni at each, then there will be differential of dNi. So Ni differential of log Ni plus log Ni times differential of Ni. Okay. And that will be equal to 0. Okay. Now you can see that this dNi is contained in all terms, because when we will take the differential of this log Ni, there will be again dNi, because the differential of log Ni will be what? This will be 1 over Ni times dNi. Okay. This is differential of log Ni. So you can say that dNi is contained in all terms. So we have taken this dNi as a common factor. Okay. And this sign of summation has been also taken outside of this square bracket. So it is operated in on all terms. So the first term remains what? After taking this dNi as a common factor, the first term is log Gi minus Ni times differential of differential of log Ni, and so this will be Ni times 1 by Ni into dNi, but dNi has been taken as a common factor, and in last term when you will take dNi as a common factor, the remaining term is what? This is log Ni. Since here is minus sign, so both of these two terms will become minus. So I have written this minus Ni into 1 by Ni minus log Ni. Okay. Now this Ni and this Ni will cancel out. So what is your result? This is summation over I log Gi minus log Ni minus 1 is d and I is equal to 0. But as you know, in a statistical system, this Ni is a very large number. So its logarithmic value will be also very large. And so this is much greater than 1. Or in other words, you can say that 1 is much smaller than ln Ni. So we can neglect this number 1 in comparison to this ln Ni. So after neglecting 1, your result is what? This is summation over I ln Gi minus ln Ni dNi is equal to 0. Okay. So after simplifying this result, we have obtained this equation number 5. Now, as I have told you earlier that we are considering an isolated system which neither exchange particle nor energy with the surrounding. So the total number of particles and the total energy of this system will remain constant. And as the total number of particle is constant, so you can say that total number of particle n, which is equal to n1 plus n2 plus so on plus ni, or you can write it in brief, summation over ni, this is equal to constant. Okay. So total number is constant because system is isolated. So when we will take the differential of this n, that is dn, so summation over I dni will be equal to 0. Okay. Again, as the total energy of the system is also constant because we are considering the isolated system. So if you write the total energy by the symbol U, what will be this U? As you have learnt earlier that among the group of particles N1, each particle has energy E1. Each particle. Okay. So the total energy of this N1 particles will be what? That will be N1 E1. Okay. Because among these N1 particles, each and every particle has same energy and that is equal to E1. So the total energy of the group of particles N1 is equal to E1. N1 E1. Similarly, the N2 particles will have total energy N2 E2. Nn particles will have total energy Nn En. So when you will sum up all these energies, you will get the total energy U. So U is equal to N1 E1 plus N2 E2 plus so on Nn En. And in brief, you can write it as summation over I Ni Ei, and this is equal to constant. Okay. So when you will take the change of this total energy, that will be 0 because total energy is constant. So you can write summation over I Ei dni is equal to 0. Okay. Now actually here we used a concept which is known as Lagrange undetermined multipliers concept. Lagrange undetermined multiplier. Determined multiplier. We use the concept of undetermined Lagrange undetermined multiplier to evaluate this result, to find this result. And in case of Lagrange undetermined multiplier concept, what we will do? We simply multiply this equation 6 by a parameter alpha. Okay. And this equation 7 by beta. Actually, these alpha and beta are called Lagrange undetermined multiplier. What will be the value of alpha? What is beta? All these things will be identified in the forthcoming lecture. Here we are simply considering that these alpha and beta are two parameters which are called Lagrange undetermined multiplier. So let us multiply equation 6 by alpha and equation 7 by beta. And after multiplication, we will add these two equations, that is 6 and 7, after multiplication by alpha and beta, we will add these two results in this equation number 5. We will add. Since you can see that even after multiplication by alpha, the result in RHS, which is 0, will remain same. And even after by multiplication by beta, the in RHS of equation 7 will remain 0. So we can add these two zeros in the first result, and so there will be no change. The RHS will even remain 0 after adding these two terms. So you can see in LHS there is what? There is summation over I log gi minus log ni dni. Okay, and this is 0. And when you will add these two equations after multiplying by alpha and beta, the result in RHS will be 0 at each, and that will be what? This is summation over I log gi minus log ni plus alpha plus beta ei dni equal to 0. Okay. Now, since each dni is not equal to 0, summation dni is 0. Summation dni is 0. But you cannot say that this dni is 0 because dni has different values, dn1, dn2, dn3 and so on. Okay. Or in other words, you can also say that this dni is an independent variable. So for all values of dni, this equation will hold only when the term inside this square bracket will be equal to 0. Okay. So you can write this ln gi minus ln ni plus alpha plus beta ei equal to 0. Okay. And as you know that this ln gi minus ln ni, this will be what? This is ln gi divided by ni. Gi divided by ni. And this log gi by ni can be written as minus log ni by gi. You know? Yes or no? Definitely yes. So log gi minus log ni can be written as minus log ni by gi, and plus alpha plus beta ei equal to 0. Now, when you will take this alpha plus beta ei in RHS, there will be a minus sign. In LHS, there is also minus. So both of these minus sign will cancel, and your result will be what? That is log ni by gi equal to alpha plus beta ei. Okay. In some of the books, you will find that actually these two results are 0. So in some of the books, you will find that without adding here these two factors, they have equated the equation 5 with the sum of the equations 6 and 7. In that condition, the sign will be just opposite. Here we have obtained that log ni by gi is equal to alpha plus beta ei, but in those books you will find that log ni by gi equal to minus alpha minus beta ei. You will find that is also correct. That is also correct. Okay. You can do like that. So as a log ni by gi is equal to alpha plus beta ei, so you know from definition of logarithm that ni by gi will be equal to exponential e to the power alpha plus beta ei, and that can be written as e to the power alpha times e to the power beta ei. Now this factor e to the power alpha is denoted by the symbol capital A in general. So, and you have learnt earlier that ni by gi is what? This is simply the average number of particles per quantum state. And this is called occupation probability, and it is denoted by the symbol f of ei. So f of ei is equal to a times e to the power beta ei. Okay, a times e to the power beta ei. But as I have told you that in case of classical system, the energy levels are almost continuous. So for continuous energy level, continuous energy distribution, we will drop this subscript I and simply write, instead of f of ei, we will write f of e. So this f of e will be written instead of f of I. F of ei. Okay, this will be just okay. Page has been turned again. So now, as you can see, this parameter beta I have not evaluated here, but when in the forthcoming lecture we will evaluate the value of this beta, you will see that this beta comes out to be minus 1 by kt. But as I have told you earlier, that some of the books you will find that this f of ei is equal to e to the power minus alpha into e to the power minus beta ei. This is just for the making the calculation in some different way. But this is also correct. It is not incorrect. So in all those books where you find that f of ei is equal to e to the power minus alpha into e to the power minus beta ei, in that book you will find that this beta is equal to 1 by kt, not minus 1 by kt. But when we make the algebra in such a way that we find that f of ei is equal to e to the power plus alpha into e to the power plus beta ei, then beta is found to be minus 1 by kt. This is the difference. Both of these values will be correct. This just depends on making the calculation. Okay. So this f of ei you can write a times e to the power beta ei. Now beta is equal to minus 1 by kt. So this will be e to the power minus ei by kt. And as I have told you that since in practice in classical system, the energy levels are almost continuous, so we will drop this subscript I and we will simply write f of e equal to a e to the power minus e by kt. Actually k is Boltzmann constant. So this is the expression for the distribution function, and this is actually called Maxwell Boltzmann distribution function. We also say that this is Maxwell Boltzmann distribution law. Actually, for energy E, how many particles per quantum state will have energy E, this equation represents. So this is also known as Maxwell Boltzmann distribution law. And the statistics resulting from this distribution function is called Maxwell Boltzmann statistics or classical statistics. So this expression for the distribution function is the basic result or basic equation on which the Maxwell Boltzmann statistics is established. And so whenever we will now discuss in the forthcoming concepts of Maxwell Boltzmann statistics, always we will need the expression for this distribution function, and this will be always used to deal with any theory, any problem. Okay. So I hope you have definitely understand the different steps for the calculation of this distribution function, and definitely you have enjoyed this video. So definitely you should watch the video seriously and write down all these things in your notebook, and then you will see that I have written each and every step for your convenience. I cannot write the language, okay, but I have written almost all the language too, because you will be convenient and you can write in your examination directly, just just as a good notes. So, uh, thank you very much.